Hello, so by popular demand, we're going to do a video working a limiting reactants problem. Before we get into limiting reactants, we need to make sure we understand this map of relationships here that we covered in class, particularly this part over here on the left. This describes the relationship between the mass of a compound and the moles via the molar mass. The molar mass tells us how many grams there are in a mole, or grams per mole. So we can convert from mass to moles or from moles to mass. And if we want to go from moles to mass, we multiply by the molar mass. If we want to go from mass to moles, we divide by the molar mass. So that's the first important part. The second important part is the relationship between moles of compound A and moles of compound B. These could be, for example, a reactant and a product, or two reactants in a balanced chemical equation. The mole conversion is done through the ratio of the coefficients of the balanced chemical equation. Okay, we'll pause here if you want to review that. Okay, so if we're ready to move on, let's think about this guy again. Okay, so we'll do an example with the monsters. Right? Frankenstein wants to manufacture some monsters. He has in his warehouse 217 heads and 632 arms. Somehow it always seems to make more sense when we talk about the heads and the arms rather than actual chemicals. So we'll run through the procedure here. And he has those heads and he has those arms, and he has an unlimited supply of other body parts, so we're just going to ignore them. And we're going to make this kind of pretend balanced equation. One head plus two arms equals one HDARS2, which is one monster. And of course the ones are grayed out because in a real chemical equation we don't put in the ones. They're kind of pretend. Okay, the first thing we're going to find out is what's the limiting reactant. Does he run out of heads first, or does he run out of arms first? We're going to calculate how many monsters could be made first if all the heads are used, and second if all the arms were used. Whichever one is smaller, right? Whichever one gives you a smaller number of potential monsters, that one is limiting. That one runs out first. Okay, so let's do this. Okay, if all the heads are used, we're going to remember, think back to that first slide with the map. You need to go from, use the balanced chemical equation and the coefficient ratio to relate reactant to product, right? So one head gives us one monster, two arms gives us potentially one monster. Okay, so let's start with the heads. We have 217 heads. And one head is able to give us one HD ARS2. Right, one head gives us one monster, and then the heads and the heads cancel, and that gives us 217 potential HD ARS2. Okay, then for the arms, we have in the warehouse 632 arms, and we use the coefficient 2 arms produces 1 HD ARS2. Okay, and that we're going to cancel now the arms and the arms, right? So that's why the arms goes in the denominator here. So it can cancel with the arms here. And we get 632 times 1 over 2, 316 HD ARS2. Which one is smaller? Well, of course, the HDARS2 is small. 217 is smaller than 316, and so the heads run out first. I run out of heads before I run out of arms, so heads is the limiting reactant. Okay, the next question after identifying the limiting reactant is, what is the theoretical yield? How many monsters can he make? And how many can he make? He can make the smaller one out of these two numbers, which is 217. Right? Because once you get to the 217th monster, you're out of heads. Doesn't matter that you have more arms, doesn't matter that you have more legs or more torsos, you're out of heads. Can't make any more. And so the theoretical yield in terms of the number of monsters is 217 monsters. Very often, the theoretical yield question in real life doesn't say how many molecules or how many moles, but what mass. And we can answer this for the monsters also. Let's say each monster weighs 100 kilograms. How many kilograms of monsters can we make? Well, if we have 217 monsters, and each monster has a monstrosmolecular weight of 100 kilograms per monster, and then we multiply just like we do on that map, right? To get from moles to grams, we multiply by the molar mass, grams per mole. Here it's kilograms per monster. The monsters and the monsters cancel, and we get 21700 kilograms of monster. And if we want to do it with the right significant figures, it would be 2.17 times 10 to the 5th kilograms. Okay. Finally, we can find out how much excess reactant is left over. I'm going to show you the way we did it in class here, and later in the slideshow, we're going to show you a little shortcut. Either way, the most important thing that we need to find out is, in order to find how many unused arms we have to find out how many arms we used. Right? We know we have 632 arms to start with. We used a certain number, and we have a certain number left. And so the arms used is going to be as follows, right? We can use the same procedure and relate arms to heads, right? Use the same procedure as we did here. We used up, we used up all 217 heads. How many arms came along for the ride? Right, so we do 217 heads And then now we use the ratio between arms and heads, right? So one head requires 2 arms. The heads and the heads cancel, and we get 434 arms used. Okay, so we used 434 arms. We started with 632 arms. And so now we're going to do this. We're going to say we started with 432, nope, not 432, 632 arms. That's what we started with. And then we're going to subtract the 434 arms that we used, and we wind up with 98 arms remaining when the reaction is done. No, not 98, 198 arms remaining when the reaction is done. And so that is what we call the excess. The excess reactant is the arms, and how much left over, or how much excess we have, is this number here, 198 arms. Okay, so let's do a real one now. This is the problem we looked at in class. 3 hydrogen plus 1 nitrogen gives us 2 ammonia. And we mix 5 grams of nitrogen with 3 grams of hydrogen. We want to find out first, what is the limiting reactant? Second, what's the theoretical yield? In other words, how much product can be made? And 3, how much excess is left over? We're going to follow basically the same procedure, the same train of thought as with the monsters. So to find the theoretical yield, and along the way identify the limiting reactant, we're going to calculate the possible amount of product formed for the first reactant, which is hydrogen, and then do the same thing for the second reactant, which is nitrogen. And whichever reactant gives the lower yield is the limiting reactant. The amount of product that you get from that limiting reactant, right, whichever one is lower, that's the theoretical yield, because one of the reactants, the limiting reactant, ran out. Okay, so to do this, remember what we need to do. We need to go from grams, right? We're given grams, and according to that map in this first slide, the first thing we need to do is use the molar mass to go from grams to moles, and then use the coefficients to go from moles of reactant to moles of product, and then use the molar mass of the product to find the grams of the product, which is the yield. Okay, so let's do the first one, which is nitrogen. If all the nitrogen reacted, well, we would take our 5.0 grams of nitrogen, and if we liked, we can put it over 1, and then we divide that by the molar mass. So we do divided by 28.014 grams per mole, and the grams and the grams cancel, right? And so now we have moles of N2. Next, we need to use the coefficients, right? And we need to get from N2, we use the coefficient over here, 1, and then from N2 to NH3, so 1 to 2, we put the N2 down here in the denominator because we want to cancel our N2s and want to be left with NH3. And so we cancel our N2 and our N2. Now we have NH3, and we want to get from moles of NH3 to grams of NH3. So we're going to multiply by the molar mass of NH3. So we're going to set 17.031 grams per mole of NH3. And so what happens now is our moles and our moles cancel. What do we have left? We have grams of NH3. And we do the math out, and we get 6.1 grams of NH3. Now we can do the same thing for the nitrogen. We start with, hydrogen. We start with 3.0 grams of H2. If we like, we can put over 1. We use the molar mass of H2, 2.016 grams per mole. We use the coefficients, 3H2, 2NH3, and finally we use again the molar mass of NH3, and then we cancel grams, grams, hydrogen, hydrogen, moles, moles, and we get grams of NH3, and when we do the math, we get 17 grams of NH3. And which one is smaller? Of course, the 6.1 is smaller than 17. And you can see in this slide, we've changed all my scrawl into actual readable text. .1 smaller, less than 17. So what does that mean? That means N2, right, N2 that gave us the 6.1 grams is the limiting reactant. And the theoretical yield is, in fact, 6.1 grams of NH3. Okay, so the next question is, how much excess reactant is left over? How many heads, if we're looking at Frankenstein, how many heads are remaining when we're done making monsters? How much H2, which is the excess reactant, is left after we finished making the NH3? Right? Not all the H2 got used up. If it did, we would have made this much NH3, 17 grams. Couldn't do that. So we ran out of nitrogen once we got to 6.1 grams. Okay, so the first thing we need to do is find how much excess was actually used up. And I showed you a way to do it with the heads and the monsters. We're going to use a little bit of shortcut here. And so what we're going to do is we're going to multiply the starting amount of excess, 3.0 grams, by the ratio of the theoretical yield, how much was made, to the possible product formed from excess, right? So 6.1 over 17, the theoretical yield over the possible amount made by excess. And so we do 6.1 over 17, right? That's the ratio here, times 3.0 grams. That's the starting amount of excess. And when we do that, we get the amount that's consumed, 1.1 grams. Okay, once we know how much got consumed, how much actually got used up, we subtract that from the starting amount, and we get what's left. Right, so we have the starting amount, which is 3 grams, and then the amount that was used up, 1.1 grams. We do the subtraction, and we get 1.9 grams of H2 left over. All right, so we finished that problem. Now, here is another problem. Okay, so here's the next problem that we're going to do. We have one MgCl2 reacts with 2 AgNO3. Right? Magnesium chloride reacts with silver nitrate to give us magnesium nitrate and silver chloride. This is a precipitation reaction, right? So we could use this for example, in a gravimetric analysis, something like that. Okay, and so the problem is 4.11 grams of magnesium chloride react with 5.67 grams of silver nitrate, and we want to find the limiting reactant, the theoretical yield of silver chloride, and the excess reactant. Okay, so you'll notice that there is magnesium nitrate and silver chloride as products. Because the question asks about silver chloride, we're going to use the silver chloride as the product in all of our reactants, and we're just not going to do anything with the magnesium nitrate. Okay, so this problem is set up just like the ammonia problem in the last slide, but as you can see, it's blank. And the answers are here. The answers are not exactly what's important. What's important is the process. So go and pause the video, write this down, and try to do it yourself, and see if you get the same answers that I did. Okay, so here's the last part of the problem, which has to do with the excess reactant. And again, I've set it up like I did for the ammonia problem. So you can pause the video now, try it yourself, and see what you get. All right, that's all for now. See you in class.